All right. So this is a quick review for your Unit 2 test on scatter plots, correlation, and least squares regression lines, and residuals, and all that good stuff. So number one, researchers studying growth patterns of children collect data on the heights of fathers and sons. The correlation between the father's heights and the heights of their 16-year-old sons is most likely to be, well, you got to figure there is some type of correlation. So you're not going to say near zero. You also say somewhat greater than one. It can't be. Correlation has to be between -1 and 1. Uh, it's probably not perfect exactly, so I'd also probably get rid of D, and for that reason A, but I'd also get rid of A because it's going to be likely a pretty positive correlation where taller fathers will probably have taller sons. So C is the best answer there. The auto insurance industry crashed some test vehicles into a cement barrier at speeds of 5 to 25 miles per hour to investigate the amount of damage to the cars. They found a correlation of 60 between speed and damage. If the speed at which the car hit the barrier is 1.5 standard deviations above the mean in speed, we expect the damage to be so expect the damage to be blank, the mean damage. So we're saying speed here as X and damage as Y. So the speed to be 1.5 standard deviations. So that's the z-score for our X variable, which means we'll use the equation. Z for Y predicted is correlation times ZX. So 0.6 times the 1.5. Plug that in. I think we should get D, 0.90 standard deviations above. 3, which scatterplot shows a strong association between two variables, even though the correlation is probably near zero? Remember, correlation is strictly measuring linear patterns. So A is a pretty good correlation. B, not as much, but still probably correlation. D, a negative correlation. E, no association, no correlation at all because there's no pattern. But C is the one you should say here, that it has practically no correlation, though there is an association of a good curve right there. 4, the correlation between X and Y is 0.35. If we double each X value, decrease each Y by 0.20, and interchange the variables, meaning put X on the Y axis and vice versa, the new correlation is, you have to think about how you would find R by hand, and that was all based off of z-scores. Since they're all standardized, decreasing Y and doubling each X, it doesn't really matter. Since correlation is based off of z-scores, if your R was 0.35, your R still is 0.35. A consumer group collected information on HD TVs. By the way, number 5, this problem is a bit dated. So anyways, just be aware of that. They created a linear model to estimate the cost of an HD TV in dollars based on its screen size in inches. So price based on its screen size. And you would think the larger TVs, the more expensive they'd be. And that was even more true probably when HD TVs first came out. In the years since this was published, you'd think that the prices come down considerably. What is most likely the value of the slope of the line of best fit? Well, so textbook says 70 because when this was released, they were just considerably more expensive. Nowadays, you actually probably want to say something like B. I just pulled this up really quick. When you're looking at like a 43-inch for, less than $300, just think about, maybe 43. If you had 43 inches and it was somewhere around $300, does it make more sense 43 times 7 or 43 times 70? Which one's closer? So hopefully you can at least assume these are all bad answers, and then you're picking between these two. Textbook says C. I think B is probably a little bit more reasonable now. The correlation between a family's weekly income and the amount spent on a restaurant meals is found to be 0.3, which must be true. Families tend to spend about 30% of their incomes in restaurants. That's not what correlation tells us. That's a nay. 0.30, in general, the higher the income, the more family spends in restaurants. R is a weak to fairly no correlation, but in general, that is saying that it is a positive R, so we can say 2. Oh, actually, I shouldn't do that yet. The line of best fit passes through 30% of the income X for restaurant spent Y data points. That's also not what correlation tells us. Medical researcher finds that the more overweight a person is, the higher their pulse rate tends to be. In fact, the model suggests that 12-pound differences in weight are associated with differences in pulse rate 4 beats per minute, which is true. The correlation between pulse rate and weight is 0.33. Well, I mean, what it's looking at is the 12-pound differences leads to 4 beats per minute. Well, 4 divided by 12 is that 0.33. But what I actually just found right there is not correlation. If you lose 6 pounds, your pulse rate will slow down 2 beats per minute. The problem I have with that one is that it says it's a for sure thing when this should be just a prediction. So I'm also going to get rid of this. Even though, 2 beats per minute for 6 pounds, that is an equivalent ratio right here. The problem there is that it's saying it will, not we predict it will. 3. A positive residual means a person's pulse rate is higher than the model predicts. That is like definition of residual right there. So I'm going to say yay on that. How much time do I have on here? 7. Oh, good. Okay. 8 is a little bit tougher than what I'd probably throw on a test, but it's fair game for AP. So education research consistently shows that students from wealthier families tend to have higher SAT scores. The slope of the line that predicts SAT score from family income is 6.25 points per thousand, and the correlation between the variables is 0.48. The slope of that line predicts that the slope of the line that predicts family income from SAT score in thousands per point. This one essentially is saying what happens when you reverse the X and Y and what would the new slope be. So slope does change when you switch your X and Y, and for that, as long as the slope is not 1, I guess. So slope comes from R SY over SX. So we know that the old slope was 6.25, and that was 0.48, and it was SY over SX. If you just divide both sides by the 0.48, then you'll get 1302. And that's equal to the ratio of your standard deviation Y over standard deviation X. But if you want to switch the variables, go ahead and switch that. If 1302 is SY over SX, just do 1 over 1302, and that will then be your SX over SY. Do that quick reciprocal magic, and it's 0.0768 is SX over SY. So now we can actually find the new slope after switching the variables, and that is SX over SY, which we know, times R, .48 times 0.0768, and that will come out to 037. I'm going to continue the rest on the next video.